Dude, I remember wanting to work on wiring materials. Good time. Before I was crushed.
So it should be forest.
Sorry? You didn't?
That's me walking down the stairs.
Okay, you said it.
You guys all set?
Okay, great, thank you. Let's wait for a couple more minutes because we see that 2 months.
I've observed. Well, I'm not a crazy person like you don't.
I was gonna say I took on average 5 classes.
Well, I would take 4 classes. They don't come as always. Never done 5.
Excuse you.
Well, I did. I've done 5 physics classes. I've done. I did 4 physics classes. That was awful. That was so bad.
The sleep of people, it would be over. See if there is an interruption at some point, and then we'll start. Okay, so it's a very great pleasure for me to introduce our today's speaker, Professor Eslam Khalaf. So in old time, we had a very good tradition. When a new faculty member would come to any physics department in the Greater Providence area, we would invite that person here so that we know new people in our area. And so, of course, it's quite fits that as soon as Professor Khalaf started his tenure at Harvard University, we should invite him here as a new professor in the great area of our city. Now, so Eslam got his undergraduate degree in electrical engineering, not physics, from German University in Cairo. But then he moved to Germany to the Max Planck Institute at Stuttgart, where he actually switched to physics. He got his master's degree in physics in 2012 and his PhD degree in physics in 2017. And that was really an exceptional PhD degree because he won the Otto Hahn medal that is awarded to the very best PhD in the whole of Germany. And then it took him just 2 very short years to get a visa to the United States, where he was invited as a postdoc to Harvard. During that time, he existed as a postdoc at that very Max Planck Institute. He spent a few years at Harvard as a postdoc, and in 2022, he moved as an assistant professor to the University of Texas in Austin. But with that year, people at Harvard realized that they really cannot exist without Eslam Khalaf, so he was invited back now as a Harvard professor. His research interests are quite broad. He actually started in disordered systems, topological and non-topological, and did some very important contributions in that field. But then he moved to topological insulators and eventually to Moire systems. And today we will learn some of very exciting work that he recently did on that topic. So let us welcome our speaker.
Yeah. Thanks, Dima, for the really nice introduction. Probably the longest introduction I've ever had. The talk I'll discuss, the talk of my talk today is about kind of a general framework to understand interactions in topological flat bands that is motivated by the problem of Moire systems and builds on a lot of insights from the quantum Hall problem. But as you will see, that this although we get flat and topological bands in these systems, their physics could be much richer than the quantum Hall physics. And in many cases, we need to kind of develop novel perspectives on that old problem to be able to account for this richness and complexity. And my talk will be roughly divided into 2 parts. In the first part, I will discuss and kind of review older works, and older by Moire standards means like 1.5 to 2 years ago. And then I will discuss more recent work, so like stuff that are most of it is unpublished. So let me start by the broad motivation. So this field really exploded by the discovery done in an MIT group led by Pablo Jarillo Herrero, where they considered twisted bilayer graphene, which consists of two sheets of carbon twisted relative to each other by some twist angle theta. And when this twist angle theta is around 1 degree, band structure calculations indicate the presence of two very flat bands around sharp neutrality. And these two bands per spin per valley, so it's 8 bands in total. And what Pablo's group did was that they manufactured the system, they measured the conductance as a function of the carrier density, and what you see here and here are just the cases when the flat bands are completely filled or completely empty, so you get a band insulator, but they also found that they get an insulator at non-integer fillings, so at some fractional fillings of the band, particularly at half and plus half and minus half. But that's of course measured in multiples of 4, so these are 8 bands, so this is really 2 electrons per Moire unit cell, and this is 2 holes per Moire unit cell. So they got these insulators that have to be attributed to correlation because the bands are partially filled. Furthermore, when they considered a 4-terminal setup instead of a 2-terminal, so to look for superconductivity, they found that this insulator is actually flanked by 2 superconducting domes. In the 5 years since then, the family of Moire materials have really expanded, and now we have a lot more Moire systems, although twisted bilayer graphene arguably remains maybe the most interesting and most difficult one to understand among them. So in twisted bilayer graphene, in addition to the correlated insulators and superconductivity, there's also the observation of quantum anomalous Hall effect, which is like quantum Hall effect but without magnetic field. So time reversal symmetry is spontaneously broken. This was in samples which are aligned with the hexagonal boron nitride, and this is actually important. There was also observation of fractional churn insulators, which are the analogs of quantum Hall, fractional quantum Hall effect without magnetic field, but these were observed at actually a small magnetic field. So it's a much smaller field than you would typically get them, but not zero field. This family was expanded actually based on our theoretical proposal, and I will discuss this a bit later, to these multi-layer systems where you choose the twist angle to alternate between positive value and minus value. And these systems turn out to be also superconducting. Actually, superconductivity is more robust there. And there's some signatures of also the correlated insulators, although these are kind of hidden behind the fact that the flat bands in this system coexist with some dispersing bands. So you really need to deduce their existence kind of indirectly. Then there is a large other class of Moire systems that is, broadly speaking, based on a Bernal Bernal subsystem. So for example, you can take a monolayer twist on top of a bilayer. Bernal is a specific specific stacking of bilayer graphene that is actually the energetically stable bond. So you can do mono on bi, you can do bi on bi, you can also do AB or ABC, like many layers on top of a hexagonal boron nitride, which form a Moire heterostructure. And for a while, it seems that this is a more boring system than others because it showed correlated insulators, but nothing else. However, very recently, a group from MIT has found if you take 5-layer ABC pentalayer on top of HBN, you get quantum anomalous Hall effect, and you get fractional quantum anomalous Hall effect. So fractional Hall effect at zero field. And finally, there's another huge family of transition metals like chalcogenides, which are two-dimensional semiconducting materials. You can also introduce a twist and get a Moire, and people have also observed correlated insulators, quantum anomalous Hall, and very recently also fractional quantum Hall effects. But I will mostly focus on the graphene family. But some of at least the considerations I discussed are also applicable to TMDs. So the first step in understanding these systems, and in a sense, we have this kind of jungle of different Moire systems. We want to bring some order to this jungle. And the first step is just to think of some set of flat bands. The first common feature in all Moire systems is that there's a valley degree of freedom. So at low energies, at the energies relevant to the Moire system, you can really split the bands into two sets of bands that live in opposite valleys. Now, an important observation is that time reversal symmetry doesn't act within a valley, but it maps the two valleys to each other. This means when I look at the bands in a single valley, they don't have any time reversal symmetry, so they are allowed to have a finite Chern number. So they don't have to, but in a lot of cases they do, and that's the case I will focus on. So I always assume there's some finite Chern number per valley. Now, if there's no other symmetry, that's the problem I have. So I have one band per valley, and they have opposite Chern numbers. And that's typically the case in twisted TMDs. But when I have spin rotation symmetry, like the case in graphene, because of their very weak spin orbit coupling, I will get a different case where I get a spin degeneracy in each valley. So I get 2 and 2. Now it turns out that twisted bilayer graphene is even more complicated because it also has a twofold rotation symmetry that gives you an extra degeneracy. And to understand this, I mean, you can see this. Like I just told you earlier that we have 8 flat bands, but here there's only 4. But it turns out you can also understand these 8 flat bands from this perspective. But to do this, you need to work a bit harder. So here I'm showing just how the bands look like in a single spin and valley, so in a single flavor. And because I have 2 bands, I cannot really, and they are touch. If I compute the total Chern number, it will be 0 because I have the combination of twofold rotation and time reversal. But there is a more refined way to define the topology of these bands, which is to introduce the non-abelian Berry curvature, which is 2x2 Hermitian matrix that captures this topology. And because this has to be odd under C2T, I can restrict its forms. Actually, depending on the basis I choose, it will always be proportional to one of the Pauli matrices, which means that I can go to a basis that diagonalizes this. And in this basis, these 2 bands look like a band with a positive Berry curvature and a band with a negative Berry curvature. And if I integrate those, I get Chern plus and Chern minus. But the important thing to notice is that the Hamiltonian itself, the single particle term, is all diagonal in this basis. So really, this is mapping this band structure to 2 opposite Chern bands that are connected by some single particle tunneling. And the single particle comes from dispersion, which in some sense is a weak perturbation in the limit when the band is sufficiently flat. And one way to understand actually how this inter-Chern tunneling would reproduce this band structure is if I take one of these Chern bands and do a particle hole transformation, then this inter-Chern tunneling looks like Cooper pairing in a Chern 2C band. So this Cooper pair will have to have 2C vortices, which will precisely be, so it tells me that the Chern numbers have to be 1 in this case, because these 2C vortices will be precisely these 2 Dirac cones. And in fact, these 2 Dirac cones have special property that, unlike, for example, in graphene, they have the same chirality rather than opposite chirality. That makes kind of this band structure very special. It's not a band structure you can realize in a lattice model. So with this picture, we can kind of think in a more unified way about the flat bands in the different Moire systems, just based on the symmetries that exist in the system. So if I have no spin rotation symmetry and no twofold rotation symmetry, then generically I have 1 flat band per Chern sector, which is per valley, and they're related by time reversal. If I have spin rotation, which happens in graphene, but no C2 symmetry, I will have 2 flat bands per sector. And finally, if I have C2 symmetry, I have 4 flat bands per Chern sector, with the distinction that now the 2 sectors are related by C2T rather than T. And that I'm allowed actually to have tunneling terms between the 2 because they don't live in opposite valleys. So there's no there's no symmetry that really tells me they cannot couple. It's just this magic angle condition that tells me that this tunneling is small. So we have now reduced the problem to a problem that's similar to something we're familiar with. These are flat Chern bands. And there's a very famous example of a flat Chern band, which is the lowest lambda level, or lambda levels in general. So there's at least 3 effects that we could start looking for in the system based on the analogy to lambda levels. And the first one is, we know that when we fractionally fill the lowest lambda level, we get the very celebrated fractional quantum Hall effect. We know also that if we have spin degenerate lambda level and we half fill it, we would get ferromagnetism. We could get quantum ferromagnet. And this is really an effect that can be understood simply as a consequence of Hund's rule. You want to put, if you have a repulsive interaction, you want to put all the electrons in the same band to so that the orbital part of the wave function is antisymmetric, which minimizes repulsion. And finally, when we have also in quantum ferromagnetism, if we want to add charge to the system, we can just add an electron in the band that is empty. But there's actually another more subtle way to add charge, which is to form a skyrmion. So it turns out skyrmions in the system carry a charge that's equal to the Chern number times the winding number of the skyrmion. And in the quantum context, under some conditions, it turns out actually the skyrmions are the cheapest way to add charged excitations to the system. But that's an energetic statement that could be the same or different in our system, and I will discuss this a bit at the end of my talk, like the energetics. So just based on this picture, we can try to translate these insights to Moire systems and try to understand the phase diagram in terms of these. So the first thing we can ask is what are the ground states at integer fillings? We get these correlated insulators at integer fillings when counted, taking into account the Valley and spin degeneracy. So at integer fillings of the Chern bands, we get these correlated insulators. And to understand these, as I said, we can, to a first approximation, ignore the band dispersion and just think of a strong interaction projected onto these bands. So, our Hamiltonian has this form, which is familiar from the quantum Hall context, but let me say a few words about it. So this is just an interaction-only Hamiltonian that's written in terms of the density operator projected to the flat bands, and I'm just defining it relative to some reference. Sometimes, for example, in twisted bilayer graphene, you have approximate particle symmetry, so you want to define it relative to the charge neutrality point. Now, the important thing is, unlike in, for example, if you have a Hubbard model in a lattice, the density operators at different lattice points commute. Here, these projected density operators are more complicated objects, and particularly due to the topology, they do not commute. And this is the reason why, although this is an interaction-only Hamiltonian, it is non-trivial. But the surprising property is that at integer fillings, this Hamiltonian is frustration-free. And this means that although all these density operators do not commute, we can find a common set of eigenstates of them. And these are basically generalizations of these quantum Hall ferromagnets. So these are states where I choose a subset of bands to completely fill, and then the rest of the bands are left empty. And of course, I have some large U2 times U2 or U4 times U4 symmetry to rotate this manifold of states into each other. So it's a large manifold of states. Depending on the reference, usually at charge neutrality, these are actually exact ground states because they are zero modes of a positive Hamiltonian. Away from this limit, we can prove that they are low-lying eigenstates. We cannot really prove that they are ground states, but a lot of evidence from numerics suggests they are still a ground state. So let's try to see what are just the implications of this to the physics in our system. So a very simple implication we can immediately see is the following. Let's say we're considering an odd filling. So we have the bands divided into two Chern sectors, and really I can think of 2 and 2 or 4 and 4. It's the same story. If I'm at odd filling, there's no way to form a generalized ferromagnet without having an imbalance between the two Chern sectors, because I cannot really mix the two Chern sectors. It's not allowed to form a band that mixes the two. This tells me that at odd filling, I do expect correlated insulators to have an odd Chern number, so to be quantum anomalous Hall states. On the other hand, at even fillings, the Chern number has to be even, which means it can be either 0 or finite. It can be an even number, and typically there's some anisotropies that break these symmetries and actually select the 0 sector. So the first thing you would deduce from this is what I would call like a parity rule that tells me that the parity of the filling and if you have a correlated insulator, the parity of the filling and the parity of the Chern number has to agree. So this picture would be where we stop if we're thinking of systems that break C2, but for systems which have C2, the leading perturbation we can add to this picture is the tunneling between the sectors. And it turns out there is a kind of a nice way to understand this tunneling, which is the following. So if we think of this tunneling, which comes from the flat band dispersion, if we think of it as perturbatively, as a weak perturbation to the strong coupling physics, we can think of one of three pictures. Like if the tunneling connects two empty bands, it does nothing. Connects two full bands, it does nothing. If it connects a full and empty band, we get a second order process that reduces the energy. It's basically the same thing you get in super exchange, but here I'm thinking in terms of this band picture because these bands don't really have a lattice representation. What this effectively gives me is an antiferromagnetic coupling between the sectors. And here I'm again illustrating it on the case of two bands, but you can think of adding valley and spin, so it's kind of an antiferromagnetic coupling in the spin and valley degrees of freedom. And there's a way to describe this precisely that's described in the paper. But the main lesson is that basically the pictures that you get ferromagnetism within each Chern sector, but antiferromagnetism between the sectors when you switch on this coupling. And that's a picture that actually have been confirmed in numerous numerics by now. So starting from Archie Falk, but then there has been some exact diagonalization work, some DMRG on cylinders, and some. So all of these have their limitation. There was also quantum Monte Carlo work, which actually it turns out that the system at charge neutrality is sign problem free, so you can do Monte Carlo, and it did verify this picture. It recognized exactly these states with the right energy split between them. So the next thing we can ask is about charge doping. And it turns out in this system, because of this topology, there could be very interesting scenarios for charge doping in addition to just adding a single electron or a single hole. Because of the relation to the quantum hole picture, we could, of course, add charge as an electron, but we could also add charge as skyrmions. But we find that we have two options. We can add a skyrmion in the Chern plus sector or an anti-skyrmion in the Chern minus sector. And because the charge is the product of the Chern number and the winding number, when we flip both, we get the same charge. However, once we add a coupling between these two sectors, the surprise is that we immediately get pairing. So when we add this tunneling, which as we said, it had to exist in this system. It just comes from this dispersion, which is never zero. It's always finite. This gives me an antiferromagnetic coupling that wants a skyrmion and anti-skyrmion to sit on top of each other, but they do have the same charge. So this will generally lead to the formation of a charge 2 object. And maybe one more kind of detailed way to see it is that if I look from the side at a skyrmion in one Chern sector, these are not layers really, these are Chern sectors. And on Chern sector and anti-skyrmion on the other Chern sector, when they're sitting right on top of each other, this antiferromagnetic coupling is happy. When I start to move them apart, I will pay an energy that's proportional to the distance squared. So it's really a confining potential. And even if I keep a completely unscreened Coulomb repulsion, which is 1 over R, and regardless of how the prefactors, like the ratio of the prefactors, this term always wins. So I always get a bound state. So this is in a sense a very kind of remarkable result because at least the first step of this calculation was just aimed at understanding the insulators, but we got kind of the superconductor for free. We didn't really have to add anything or change anything in the theory to get it. Of course, charge 2e bound state is not exactly a superconductor. We still need this object to condense. But it does turn out there is actually also a neat argument to show that this compound object actually has a finite mass, has a finite effective mass. And to see this, you just think of these skyrmion and anti-skyrmion as two objects that have the same charge E. They are connected by some spring force, J, and they feel opposite magnetic fields because they live in opposite Chern bands. They feel opposite effective magnetic fields. Now, when this object starts moving, there will be an opposite Lorentz force that tries to pull it apart. but this will be matched by a restoring force that tries to pull them together, which tells me that the moving object will have an energy that is proportional to the velocity squared, and I can read off the prefactor as the mass of the pair. And from this mass, I can estimate a Kosterlitz-Taulis temperature for the condensation of this object, and it turns out to be controlled just by the scale. And if I put some realistic parameters in, I get actually something on the right scale, so around 1 Kelvin. So this is kind of a new it's kind of a mechanism of superconductivity that really relies on the topological structures of the band. It doesn't have analog and Landau level systems because we always have one Chern sector or the other. But also it really needs the topology, so it doesn't have a simple analog and lattice models either. And of course, this is a cartoon calculation. You can do a more kind of serious large N field theory calculation to verify the same picture. And also there has been nice GMRG work from Mike Zaltel's group. But what they did is that they really took two Landau levels that are in opposite field and coupled them. And what they found is they get this superconducting phase. Now, one of the early successes of this story was that it actually answered a question that was a bit puzzling, which was which Moire systems tend to become superconducting. So we have twisted bilayer graphene, it has flat bands and topology, but then the assumption was that if you make any system that has some flat bands, it should be superconducting. But when people made it, they found that that's not the case. So twisted double bilayer graphene, it was thought earlier that it's superconducting, but then it was found that there is no superconductivity in this system, or at least you need to put it on certain substrate, and you get very weak superconductivity. Also in this twisted monobi, you don't get superconductivity. Also, even if you take twisted bilayer graphene itself and align it with the hexagonal boron nitride substrate, you lose the superconductivity. And the common factor between all of these systems seems to be the lack of the breaking of C2 symmetry. So the breaking of C2 symmetry removes one of the essential ingredients in our story, which was the coupling between the Chern sectors. So when it's broken, we have Chern sectors that are decoupled, so we cannot really get this pairing between these Kermian objects. And also, this led us to predict a new class of twisted multilayer systems beyond TBG that we predicted to be superconducting. And these systems, let me just say a few words about them. So these are this system that consists of multilayers with alternating twist angles. And it turns out this system has the same symmetries as TBG, in particular C2T symmetry. This system turns out to be more because its single particle physics can be mapped exactly to a collection of decoupled twisted bilayer graphenes, but with different interlayer coupling, so that feel different magic angles. For example, if you take trilayer, you can decompose it into a bilayer with a rescaled interlayer tunneling by a factor of root 2 plus a single layer. And this tells you that the first magic angle of the system will be larger by a factor of root 2. And after our work, the experimentalists had made the system at the magic angle that we described, and they did indeed find the system to be superconducting. Superconductivity turns out to be more robust in this system. And it has other advantages, like the fact that superconductivity can be tuned by an electric field. And since then, people have also observed superconductivity in the 4 and 5 layer systems. Now, this was kind of very promising early successes, and the story seemed like to beautifully capture a lot of aspects, but of course, as always, experiments always come back and challenge the theory. So let me just summarize the successes and failures of this story. So the successes were that indeed in experiment most observed correlated insulators follow this parity rule. So usually when we see quantum anomalous Hall states, they are at odd fillings, and when the correlated insulators we see at even fillings have Chern 0. there are at least some cases where the correlated insulators were proven to be ferromagnets, like through hysteresis, so they are valley ferromagnets. I didn't really discuss this, but when you apply small magnetic field, you can stabilize some Chern insulators whose Chern number is related to the filling in a very specific way, and that's something also you can get from this picture. And finally, it kind of predicted this rule that at least seems to be true in practice, that C2 symmetry is somehow important for superconductivity. Of course, there has been few discrepancies between the experiment and theory. Most prominently is that the theory predicts the strongest insulator at charge neutrality, while in experiment, usually the insulators are seen at +2 and -2, but not at 0. At 0, you usually see a semi-metal. And this is seen in most experiments except some samples from Dima Efetol's group. The theory also predicts an insulator at nu=1, but the experiment usually doesn't see an insulator at nu=1, again, except for some samples by Efetol's group. And the theory expects quantum anomalous Hall states to be much more robust than they are. So quantum anomalous Hall states seem to only be observed in HBN aligned samples, so they seem to need some extra help. But again, the exception is one sample by Efetol's.
Does the symbol still exist?
I don't know which ones are still existing and which ones were like. I think some of them are no longer exist, but some still exist. But there is a plausible explanation that doesn't rely. There's a plausible explanation where it's not just like these are very exceptional samples. That there could be some reasonable difference between the Efetol samples and everyone else's. And I'll discuss this now. But yeah, I think just this is the experimental facts kind of.
But that's one Efetol samples. That's a second layer of difference. That Efetol samples and every other of his samples.
No, so usually, Efetol haven't published a lot of samples. I mean, so there's maybe 4 or 5 that are published. Most of them has a gap at neutrality. Only one seems to have something at a quantum anomalous Hall state at nu=1. There's also this aspect that actually the theory is particle symmetric while the experiment has some particle asymmetry. And that's an aspect that's not really well understood. Like, I think it's something in the description, in the microscopic description of the model, there's some terms that we haven't captured properly.
So does this all respect particle symmetry here?
Likely not. But there is a you'd have to explain, like, the insulators typically are stronger on the electron doping side than the hole doping side.
Yes.
And it also seems to depend on the angle. So at larger angles, it becomes more symmetric, and maybe even the insulators become stronger at hole side. And it also seems to depend on when the sample is aligned or not. So there is a few parameters that influence it. It's not just a simple term that you can add. But I want to say that there is a few sources of particle asymmetry that you can add that turns out not to change the results when you take the strong coupling limit. So it's not just the magnitude, the bare magnitude of this particle asymmetry, but when you project it onto these flat bands and look at the correlation physics, a lot of the time it doesn't have a big effect. That's kind of the issue. There is one thing that I would not really put it in either successes or failures, which is this picture naturally predicts fractional Chern insulators, although I will not discuss in detail the quantitative features of that, but in the experiment they are not that robust, so they require some magnetic field. So what have we been missing? So it turns out there's one obvious thing, which is not really something about a bad approximation we did for the model we started with, but it's just that we started with the wrong model, which is that we didn't assume there is a strain. But it turns out that strain is important in the system, that in particular heterostrain that shifts the 2 layers differently, that strains the 2 layers differently, is important basically because the Moire pattern acts like it magnifies. It acts like a magnifying lens of anything that's different from the layers. Because if you shift the layers, a small movement would be a very big movement for the Moire pattern. So we had some already have thought about this problem, and we suggested in this work that actually a charge neutrality strain could stabilize a semi-metal instead of a gap insulator. And there's some, I could briefly explain how this happens. So let me actually do it on the board. So like you have. Are there any pens? Okay, that's not working. Well, I can describe it in words. So we have these opposite Chern sectors, and so as I said, we are trying to form ferromagnets or orders that just that fills bands independently in one or the other Chern sector. But we could start thinking, what if we want to form inter-Chern order? So condense a particle hole between the opposite Chern sectors. Now, there is a topological reason why this object has some finite energy, basically because you can think of this particle hole between Chern sectors like a Cooper pair in a magnetic field, and these pay an energy penalty because the order parameter has to have some vortices, and there's a background field. However, it turns out that this background field is a Berry curvature, and the Berry curvature in this system is concentrated at a point, which means if you put the vortices where the Berry curvatures are concentrated, you pay very little energy for the state. Now, when you apply strain, it turns out that the state breaks C3 symmetry, so it couples linearly to strain, while all these other states couple quadratically, so it's favored by strain. And when you do the same thing at finite filling, you see that this semi-metal will give you an insulator when you take the semi-metal and have it as a finite filling. So you end up with this phase diagram, which was obtained by very extensive numerical work from the Oxford group. Well, that's a work I wasn't involved in. So at charge neutrality, you can get this phase diagram as a function of strain, and this is basically a measure of alignment with the HBN substrate. So when you're aligned, this is around 15 MeVs. So you see that at charge neutrality, you get a transition from an insulator, a certain insulator that's picked by the anisotropies called KIBC, to a semi-metal. At nu equals 1, you don't really get a metallic, you don't really get an insulator. So you start an insulator and you transition these dashed are kind of a metallic, a poor metal state. But at nu equals 2, you transition from an insulator to a different insulator. This is instead of a kind of a generalized ferromagnet, this is a kind of complicated incommensurate spiral. But if you go up in this axis and add the alignment to HBN, you can recover these ferromagnets. So this kind of gives a nice explanation for the discrepancy. And also for the difference between the different samples. So when we align with the sample with HBN, we are more likely to recover the ferromagnets. Or when we have a low strain, we also recover these insulating states at all fillings. But when we have high strain, we get a semi-metal at neutrality, you get a metal at 1, and we get an insulator at 2. And this also suggests that the difference between Effetov samples and other people's samples is that they're probably low strain samples, because his fabrication process is slightly different. It tries to remove bubbles and strain from the samples, but this reduces the yield, but gives him these slightly different samples. Of course, we need kind of more information. We need more strain characterization of his samples to make a definitive statement. But an interesting verification of this picture came from a very nice work from Malia's Dani's group. There they did really an elaborate STM scans of different regions in a sample, and they actually imaged the microscopic order on the graphene scale, and they could tell apart these different orders. So they found that these orders are associated with some Kekulé patterns on the microscopic scale, and they found that this pattern matched the incommensurate spirals in regions which are strained, which have like maybe 0.3 or more strain. They got a Kekulé pattern that matched some of these ferromagnets, but it's not this KIBC, it's a different state, it's called TIBC, in low strain regions. And more importantly, they found that they found a gap at charge neutrality in the low strain regions. So this really kind of is, for me, is a very clear evidence that whether you have gap path neutrality or not, that's kind of an indication of the level of strain you have in a given sample. So this kind of explains some parts of the story, so some parts of the discrepancy, but for example, it still doesn't explain why fractional churn insulators seem unstable, in particular, even in samples that have low strain or in samples that are aligned with HVN, you still don't really get the fractional churn insulators. So to understand these, we need kind of a more in-depth understanding of flat churn bands, in particular, what aspects of flat churn bands resemble Landau levels and what do not, and what are the implications of these aspects. So there's roughly three. I mean, of course, there's the dispersion. So that's if we say the band is flat, then we're assuming that at least there's no single particle dispersion. So there's a few differences between the lowest Landau levels and the flat churn band. The first one is that lowest Landau level is churn number 1, but the flat churn band can have any churn number. And this has some interesting implications and interesting physics, but I will not get to talk about this. Then a very important property of the lowest Landau level, and this especially about the lowest Landau level, it's not realized in higher Landau levels, which is that it has a certain holomorphic structure. For example, in the symmetric gauge, the wave functions look like this, and they're expressed in terms of this holomorphic variable x plus iy. And a more general way to see this relation is that if I take a lowest Landau level wave function multiplied by any holomorphic function, it doesn't really get me out of the band. So I can apply the projector or not apply the projector, and I get the same result. Now it turns out that there is a class of bands that are now characterized as having a so-called ideal band geometry that shares this holomorphic structure, and that we can write models that are idealized, which means they neglect some realistic terms that ensures that the bands satisfy this property. So that's one way flat churn bands differ from Landau levels, in that they don't always have the structure, but in a sense we now have a way to measure how far we are from a Landau level by seeing how far we are from violating this condition. However, it turns out in practice that the biggest culprit in deviations from simple lowest Landau level physics in these systems, or at least in twisted bilayer graphene, is not the violation of this holomorphic structure, but it's in the fact that lowest Landau level has a continuous magnetic translation symmetry, but a band in general would have only a discrete translation symmetry. This has a very important implication. So I'm thinking of many bands, and I'm gradually filling some of them, and I'll look at the physics in the remaining bands. So if I have just Landau levels and I start filling them, every filled Landau level contributes a uniform charge density. And that comes because of continuous magnetic translation symmetry. I cannot really get anything that's non-uniform. On the other hand, when I have a filled churn band, I generally have a non-uniform charge density. And in the particular case of twisted bilayer graphene, there is a reason why this charge density is very non-uniform. What this ends up giving me is, it gives me a very dispersive Hartree. The Hartree and Fock distributions have strong momentum dependence. So usually you have a minimum at the gamma point, at the zero momentum, and there's kind of a sharp dip at gamma, and it goes up and it's a bit flat away from that. And one remarkable property that you can at least prove in some limits is that the Hartree and Fock seem to be almost equal in the system, and this has also an important implication.
Well, they're not equal here, they're actually 4 times different.
They're equal up to a shift.
Oh, so the
So it's not a multiple, that's a shift.
The exchange effect was a constant.
Yeah. That's a shift, yeah.
So the dispersion of what? A hole in the field band of...
No, I'll show now what is the dispersion of a hole. So the dispersion of the conduction and the valence band around a correlated insulator nu equals at an integer nu. For the conduction band is a plus sign and the valence band is a minus sign, so they just look like this. So at nu equals 0, it's symmetric because we don't have Hartree, we just have Fock. At nu equals 1, we have an almost flat band on the conduction side, but a very dispersive band with a minimum gamma on the valence on the conduction side. And then nu equals 2, they flip, the bands flip. So this band becomes dispersive, but still where you dope the charge is in the flat piece. But on this side, you have really huge dispersion. This is like 30 MeV, so it's larger than the Coulomb scale. So clearly, when you go to nu equals 3, the strong coupling picture breaks down because of these corrections from the field bands. And this is why, so to get a fractional Chern insulator, you needed to first polarize all bands and partially fill nu equals 3. But by the time you reach nu equals 3, you no longer had a flat band. So that's why you couldn't see a fractional quantum anomalous Hall effect in this system. And what you needed to do is apply magnetic field and magnetic field flatten the bands sufficiently to get back to a flat band where you can get the quantum anomalous Hall effect. So in the remainder of my talk, I want to kind of focus on a specific question. On how how things we learn from the Landau level picture will change when we go to a system like this, in particular when we add this effect of this dispersion. And that specific question is charge excitations. So would systems like this have skyrmion-like or non-trivial charge excitations or not? So the typical way to think about these non-trivial charge excitations, as I said, is from the field theory perspective, where you think of them as kind of long-distance smooth textures that have a skyrmionic form. Now, there is already some problems with this approach. First is, this is very inaccurate when you are at short distances. All lattice features will be kind of washed out, and as I showed you, there is important momentum space lattice scale features. Also, if I want to really compare the energetics of this object to single particles, I kind of need a formulation that deals with them, with both of them on equal footing. And for this reason, I decided to try to approach this problem from a very different angle, which is the following. So I want to think of a small skyrmion as an electron bound to a few spin flips. Strictly speaking, this is not a skyrmion because a skyrmion is really a coherent state that is a sum of all possible numbers of spin flip. But this object, when I make it larger, it would look like it would have a good overlap with a skyrmion. But for small enough objects, it's not really a skyrmion. So that's, for the rest of my talk, I'll call it a spin polaron, because it has well-defined SZ. Now, the really kind of baby version of this problem, the simplest possible version of this problem, which I call the baby skyrmion problem, is the case if you have one electron plus one spin flip, so an electron hole pair. And in this case, the Hilbert space dimension is sufficiently small that you can solve this problem by brute force. And so this would be kind of the reference to compare the more sophisticated method I will discuss later. So this is kind of an exactly solvable limit that I can compare with. But first, I want to just discuss why do we expect an electron in a Chern band to bind to a spin flip. There's actually a very transparent physical reason why this should happen, which is that it's something that's known from the early quantum Hall days, and it's a general feature actually of any Chern band, that a particle-Hall pair carries a dipole moment that's proportional to the relative momentum between them. So what this tells me is that an electron and a spin flip, in the presence of any repulsive interaction, would have a charge dipole interaction. And if the band is sufficiently flat, you expect this charge dipole interaction to form ground state. And this is something that's generic to any Chern band. Although, of course, the details of whether you get a bound state or not it would depend on the details of the dispersion and the details of wavefunctions. So I just want to tell you what will my approach to this problem be. So obviously, if I go beyond the electron plus one spin flip limit, I will have a Hilbert space that grows as the number of spin flips I add. So it's not a problem I can solve by brute force anymore. But I will show you that I will find a limit when I can solve this problem exactly. And I will construct explicit wave functions, and I will show that these wave functions are extremely good variational wave functions away from this exact limit, but they also allow me to incorporate the effects of the dispersion. So that's kind of the approach I will do. So an approach is based on the idea that is common in the quantum Hall problem, but maybe do I have how much time I have?
So definitely 10 minutes, but
Hmm?
so how much? So you definitely have 10 minutes.
Okay, I'll try to wrap up in 5 minutes. Okay, so I'll go through this part a bit quickly, but so the idea builds on the notion of pseudopotentials in the lowest lambda level, but the typical way you do pseudopotentials, which is you can think of them as really taking a short-range interaction, expanding it in gradients of in the powers of the Laplacian of a delta function, and then truncating this expansion, and then you can prove that Laughlin state is an exact zero mode of this. Now, typically, pseudopotentials are used for spinless fermions, so when in just the lowest lambda level, and in this case, the first non-trivial term in this expansion has to have the Laplacian because the contact interaction does nothing really for spinless fermions. Now, for spinful fermions, that's not the case. So it would make sense that the contact interaction is the simplest non-trivial pseudopotential. And that's something that's already been noted in an old work in the quantum Hall literature. However, the standard way to formulate pseudopotentials is in first quantization. That's very bad if I want to think of particles and holes. So I'm thinking of really a bound state of n plus 1 holes and n particles. So really we need to reformulate this whole problem in second quantization. There has been some attempts to do this, but I found that there's actually there is a different way to do it that's much simpler, which is using some coherent state basis. So I will not go into the details of this construction, but the idea is that you can write the interaction in this form. So this is a positive Hamiltonian, which means that a zero mode of the Hamiltonian is realized if and only if a state is a state that is annihilated by all of these operators M of R. I will show first that the ferromagnets are zero modes, that the holes, that the operators that create excitations, that single particle excitations like holes are also zero modes, but then I prove that there's a more complicated zero mode I can construct out of n plus 1 holes and n electrons.
So you built on this Alex Zeidel's paper here, right?
I'm not really, so I think I was motivated by their construction, but I decided to do things in a different basis because the way they did things turned out to be quite complicated. Even seeing that the Laughlin state is a zero mode for the simplest pseudopotential is an extremely complicated. So I think doing pseudopotentials in this coherent state basis where you introduce operators that are not canonical, but that commute to a projector is actually a much better way to do this problem. So using this, I can prove that this is a zero mode operator in the lowest lambda level. And I can prove that if I have a band with an ideal band geometry, which, as I argued, is a kind of usually a good approximation for any band, there's a general form of these bands that depends on a single, basically, once you know the Berry curvature of the band, you can construct the wave function. So there's these function beta of k that's periodic in momentum, k of r that's periodic in space, and they're related to each other. And if you just fix one, you can fix the other. And you can fix one by the Berry curvature. So this is just the deviation of the Berry curvature from the constant value. And I can then construct some non-unitary transformation and prove that whenever I have a zero mode of the lowest lambda level, I can always construct a zero mode for an ideal band. And from this, I can construct a zero mode operator. And at the end, I can write actually a momentum space wave function that has a complicated form for this. This is a zero mode that involves n plus 1 holes and n electrons. This is called Weierstrass sigma function. It's zero when the argument is equal to 0. But actually, there's another way to write this wave function that's maybe more illuminative. Yeah.
Is this on a torus?
Yes. Well, everything.
That's why you got the
Yes,
sigma
function. Yes. Now there's an alternative way to rewrite the same wave function, which actually is very suggestive. This looks like a pairing wave function of electron and hole, plus a single unpaired hole. And this pairing wave function, I have an analytic form for it in terms of this Weierstrass zeta function. And the advantage of this form of the wave function, well, it has kind of transparent physical meaning. It's an exact zero mode for a contact interaction because it accounts for the electron-hole interaction exactly. Electrons and electrons don't interact with contact interaction. Holes and holes don't interact. And an electron can interact at most with one hole. So if I account for single electron-hole interaction, it would make sense that I can construct an exact zero mode.
All from Savant to Zanzibar is some sort of Cauchy determinantal identity. So what's the
Yeah, the trick is the trick is to look at the analytic structure of the wave functions. Where are their zeros and their poles and their periodic boundary conditions, and use Liouville's theorem that the ratio has to be a
So
constant.
you basically guess Zens and you tell that Zens is
No,
some will be
but
having analytic functions.
that's not how I derived it. So the way I derived it was I took this wave function. So these are these C of R's that are constructed. These are these C of R operators are constructed in terms of these phi of k's. So phi of k's are would be the Bloch states in the lowest Landau level or in an ideal band. So these have the sigma functions. So I substitute here and I actually do the integral, and I use some of Liouville's tricks to do the integral. And there's two ways to do the integral. One way gives you one expression, the other way gives you another expression.
Okay, so that's how you do it.
Yes.
Because I think this sort of parallel expressions is very typical for quantum physics, and what hides behind is some combinatorics uncovered by Cauchy when he expressed some formulas with Pfaffians and S formulas without Pfaffian.
Yeah.
So, but that's not what you're doing.
That's not exactly what. So at least this expression cannot be written as a Pfaffian just because the number of electrons are always different. But yeah, it's kind of a similar kind of trick. Yeah.
But Cauchy did not use any complex analysis, so you do
Yeah.
it completely.
I do this a different way. But actually, the advantage of this expression is that you can efficiently compute expectation values of operators. There is a trick to map it to some diagrammatic expansions that I will not go into, but there is an efficient diagrammatic way to evaluate the expectation values of these. And there's one just final aspect of this wave function. It has a logarithm. It has a pole when any electron momentum hits any hole momentum. You can trace this back to the integral over space, which diverges at long distances. And of course, this would be cut off by the system size. And in the normalization integral, it's a logarithmic divergence. But this tells me that this is not really a bound state. It's actually a critical state. It's not an extended state and not bound state. It has a power law tail. But that's not surprising because it has the same energy as a single electron. But it tells us exactly what we want to do if we want to go away from that limit to any finite range interaction. If we have a bound state, we expect it to have a big overlap with this, but not have the tail. So we make this parameter a variational parameter. And you see the results. This is the variational energy as a function of this parameter. It has a clear minimum. That's for some screen Coulomb interaction. This is for one spin flip, so I can compare with the exact wave function I obtain numerically, and I see the overlap is 99% at the optimal value. I can also verify this. I compute the variational energy and the exact energy as a function of the screening length. Again, in the case where I can solve things exactly, and this ansatze works extremely well, I can go to multiple spin flips because I have an efficient way to evaluate this multi-spin flip wave function, and I can see that as I add more spin, that's in the Landau level, so as I add more spin flips, I gain more and more energetically. Of course, if I add any Zeeman term, or in the graphene context, some very small spin orbit coupling, it will eventually give me a finite energy. And I also want to mention that, here. So this optimal size parameter grows linearly with the number of spin flips. But already you can see that if I want to get even 6 spin flips, I need at least a 10 byte. So as I increase the number of spin flips, usually I need a quite large grid to simulate this energy efficiently. So it's very difficult to access these and stuff like the ED or DMRG on a cylinder. And yeah, in the context of graphene, I can apply this first to this ideal chiral limit. And I see that I have these bound states, both at neutrality and at non-zero integers, but when I dope on the heavy side, but not on the light side. So I get these states on the heavy side of doping. And when I go away from the chiral limit, I have to take into account some extra anisotropies in the system that also depend on which state is exactly selected. But so what I see is that for actually the insulator that is claimed to be seen in experiment, in the STM experiment, I see that I still have a bound state. I still have a bound state in the realistic limit at doping 2 on the pole side, on the heavy side. And I also see it on at nu equals 1, at nu equals 3, it depends on details. So the short answer is when you dope on the heavy side of the dispersion, in the flat piece of the dispersion, you get this instability. You get skirmion-like excitations. When you dope on the other side, you don't. This kind of fits with the experimental observation that usually get lambda fans indicating light quasi-particles only on one side of the correlated insulators. It also fits, but this kind of needs a bit more leaps of faith, kind of. But so in these systems, you usually have this flavor polarization transitions that happen around 2. So when you look at the whole number, it looks like you have kind of a 4-fold degeneracy that changes into a 2-fold degeneracy, and it's expected that this may happen at some point, but it usually always happens very close to -2. So when you dope a very few holes at -2, you already lose the spin polarization. So this could at least be an indication that you're doping these excitations that carry a lot of spin flips with them. So you lose the magnetization. And finally, I'll just revisit this skirmion superconductivity story. Obviously, all of this story can only be reliably applied in low strain samples. Now, in high strain samples, usually the superconductor appears on the light side, where, at least in terms of low charge excitations, they are not these polarons. Maybe they could be relevant as some long-lived resonances, but not at least the cheapest charge excitations. But in these low strain samples, usually you do see superconductivity in, well, there's not many samples, but you sometimes see it on the heavy side. And in a sense, this heavy side superconductor is probably the most exotic, like it's the more exotic superconductor because it's a superconductor that appears in a region where you don't have any evidence of light quasi-particles. It's a flat band superconductor. So this is possibly a good candidate to look for skirmion superconductivity. I also want to note that even in this experiment where it looks like this is not a very strong superconductor, when you look at it at the critical field, it actually has the highest critical field. It has the shortest coherence length, which is also what you would get from the skirmion picture. But obviously, we cannot just make conclusions based on 1 or 2 samples. We need, if we want to reliably apply theory, which we can do much better at low strain, then we need someone to be able to produce low strain samples reliably. And yeah, I just want to finish by an outlook. I mean, this approach, you can generalize it in different ways. You can, of course, look for polarons and skirmions and other Moire systems. This is kind of a new framework to understand their energetics that accounts for the lattice details. You can also start studying the different phases, also microscopically, like what is the wave function of a skirmion superconductor in terms of these wave functions and other possible phases. Also, you can, even if these polarons are not the cheapest charge excitation, in many cases they're still metastable states. So when you do this variation, there's a clear minimum. And they may have some effect in the physics because electrons can tunnel into them or Cooper pairs can tunnel into them. And also I want to mention that one of the themes I discussed in my talk is that it seems that this coupling between the opposite Chern sectors empirically at least seems to be important for superconductivity. So is there maybe a way to induce superconductivity in one of these C2 breaking systems that don't have a superconductor, that has 2 decoupled Chern sectors, by engineering some inter-valley coupling, for example, by using the substrate that has the right periodicity to scatter the 2 valleys into each other. Yeah, so this is the end of my talk. Sorry for taking a bit more time, and thank you.
Thank you.
solving for the wave function and you expanded in terms of the coherent states, were those electron coherent states or fermion coherent states?
No, they're electron coherent states. So they are, so they're coherent states in the sense that they are not orthogonal. Actually, their overlaps looks exactly like the overlap of coherent states labeled by some complex value. But yeah, they are coherent states in terms of the single particle electron excitations. Yeah.
Other questions? Actually, I have a question.
Yeah.
So you told us a story about graphene, but I wonder how much does it apply to other related materials? For example, molybdenum, halcogenogenides.
Yeah, so I think the main, so some parts apply, some parts don't apply. So the parts that apply are the ones that don't rely on the spin degree of freedom because, it's flat Chern bands, you get ferromagnetism, and when you partially fill them, all this stuff about ideal bands and the relation to fractional quantum Hall effect will be there. Now the Skyrmion physics, because you have strong spin orbit coupling, so you already assume that spin has been polarized or spin and value are strongly locked. So it doesn't directly apply. So
But this philosophy, can this be extended?
the philosophy of
this very curious Cooper pairing, is there any chance to extend it?
yeah, so the philosophy of this curious Skyrmion pairing.
Yes.
Yeah. So I think, well, you do need at least kind of 2 degrees of freedom per valley or per Chern sector. Now, maybe there's ways of stacking. I think actually, we've been thinking of a proposal like this, stacking two copies of this molybdenum ditelluride on top of each other and switching on some tunneling, and maybe there's some tunneling term that gives you the right the right energetics, the right details to get the skyrmions and skyrmion pair. So broadly, it should be it's a general framework, but we're kind of looking for the right system. It seems that twisted bilayer graphene is kind of the perfect system for it, but this effect of dispersion makes things hard, at least on the light side.
Okay, so let us thank the speaker again.
Is this thing?
So you do know Alex Seidel?
Well, I met him actually very long ago. I don't know a few of his papers for sure.
I've also read that the free Dirac cone is dual to QED3 and where the vortices are mapped onto the Dirac fields. Is that relevant in this work where you're talking about both the skyrmions?
Yeah. So here you have 2 Dirac cones that have the same chirality. So it would be kind of dual to a pair of vortices, and these form a skyrmion. So actually, if you take a vortex, but you need to also determine what happens in the core of the vortex. So it's either up or down, and this gives you something called a meron. And when you have a pair of merons with the right combination, which actually these Dirac cones give you the right combination. So you need the fact that the Dirac cones have the same chirality. So they will give you merons that add not a meron anti-meron that annihilate, but the merons that kind of add to form a skyrmion.
Right.
Yeah.
Okay.
And the merons will carry a charge E. It depends on how you want to think about it. You can think about it first in terms of a charge E skyrmion that pairs to form a charge 2E skyrmion, but also you can think of it already after in the coupled picture where you already have the Dirac cone, so then you automatically get a charge 2E skyrmion, the paired object, automatically out of this picture.
Okay. Yeah, that makes sense.
Yeah. I mean, I think there is some discussion about this in the paper. I don't remember exactly, but yeah, I think there may be a discussion.
I think I saw some names who had written the papers on that road.
Yeah.
Great. Thank you.
Okay, no, very good talk. So I'm afraid that the audience got a little bit overwhelmed by them. Elliptic functions were horrifying for most graduate students, I suspect.
Well,
so people learn these days.
Yeah, I mean, this wasn't the end, so I think you probably understand now why I kind of split the talk. So the first part of the story was kind of the easy and cool part, but I also wanted to mention newer stuff. I'm excited about these polar results because they are kind of everything worked very, very
And that's
good.
not a seminar, it's not colloquium, so it was
What?
it's not a colloquium, it was absolutely appropriate to discuss.
Yeah, yeah. Okay, that's
So,
yeah.
but I have a question about that part. So
Mm.
let's send the size of stores to the infinity. Then you will really not need an elliptic function. You can write down a simple meromorphic function, right? And maybe then with this function you play simple tricks like Cauchy,
Mhm.
and after you play them, you recreate the torus back and just write this down as a combination of functions with the, so that you get the correct Riemann surface. And maybe that's a cheap way to get this result.
My expectation is that, I mean, of course, you can think of it as a special or complicated way to write these wave functions in the lowest lambda level. But when you go away from the lowest lambda level to a flat band, you cannot write the thing as a global thing on a torus because you have these complicated periodic factors.
Yes.
Lattice, yeah, so you have complicated lattice periodic factors.
You have extremely characteristic term, which is made of elliptic functions. So
Yes.
it's not easy to manipulate. But let's just even forget about making torus and you just pile all variables close to each other so that your elliptic function can be approximated by some expansion.
Mhm.
You will still get a simple meromorphic function in place of this huge combination. Then you write it with one of the determinantal identities. And then remember, but my Riemann surface is not the Riemann surface of a simple meromorphic function. I really have to deal with an elliptic function. So I reinstate, I just select building blocks of an elliptic function and make all sorts of simple polynomials which emerge the arguments and get your second formula. I would think that's a straightforward way to do it.
Ah, okay. So this is just how to derive the first from the second.
Yes, because what you do seems surprisingly overcomplicated. That requires almost mastery of complex analysis. Now we saw that those identities are just a combinatorics.
Okay, yeah, I'm not saying that that's... So the thing is, I derived both from the integral, and it seems you can take two roots using these tricks. One of them is to combine, because you have this anti-symmetrization. So when you do...
Right, right, that's a standard thing. You anti-symmetrize a product of polynomials, and you get a different polynomial, really. That's it.
Yeah.
And that's what Cauchy tricks are about.
Yes. So, I mean, I'm not saying...
That has actually a surprisingly simple physical meaning. We once wrote a paper where we rediscovered a huge family of such identities by playing the following trick. You take a wave function that corresponds to, by bulk edge correspondence to a certain chiral edge, and then you flip all neutral modes to the opposite, and you get a different wave function. And then you try to get rid of all non-analytic factors. You got there, rewrite it a little bit, and lo and behold, you get a completely different wave function, and it's sort of physical motivated. But when you look at it, you should have exact identity if you dig deeper mathematically.
I see. Yeah, I think you can say here it's also physically motivated because the final state has a very transparent physical meaning.
Yes.
Yeah.
This elliptic function is just a way to accommodate the right Riemann surface, but all physical meaning sits in a simple meromorphic function, which should be transformable with simple combinatorics.
I agree. I think. Okay, the main point probably, the main hard step actually was constructing any representation.
Yes.
Because even either representation is extremely difficult. Like if you just write this momentum space wave function, it's very tedious to prove that it's a zero mode of the Hamiltonian. But in this second quantized coherent state representation is actually very easy. It's a few line identity, few line proof.
I guess one catch there is that you never know if you produce gapped wave functions this way. People would start with something that looks perfectly gapped, and then do anti-symmetrization and get something that's gapless. That happens in the 5-half problem a lot.
Yeah, actually, anti-symmetrization, particularly actually, the extra factor that seems harmless. It's really important.
I know that. There is a famous story of the 1-1-2 state at the Fini factor 2 source, and a wave function phase separates. It doesn't describe any quantum Hall state at all. You need to introduce extremely ugly factor to prevent that. So your story is probably a little bit like that.
Yeah. So I think it's probably what you should have guessed, because the only spin flip operator that generates a zero mode is a Goldstone mode. And there's only one Goldstone mode, and if that's the Goldstone mode, then it's just completely trivial. So this is an operator that only becomes a zero mode after attaching a hole. Although the hole itself is a zero mode, it looks trivial, but you have to attach the hole to get a zero mode to make it a zero mode operator.
Yes. Okay, so let me bring this back and then we pick up our stuff and try to have a reasonably idea. So your train is 7 p.m. sharp, right?
Yeah, let me check exactly the time because it could be 7:20 or something. So
What's time now? 5:15. Okay, we have time. We don't have the time for a very fancy place, but we have time for something like that Greek places across the road from Indian place.
Yes. Let me